Hello, Assalamualaikum warahmatullahi wabarakatuh, and good morning. Okay, for this video session, I will introduce about the HyperWorks CFD software, which is we want to run the CFD analysis. For example, you want to run the flow analysis, thermal analysis, and other types of the CFD analysis. Okay, so for new version HyperWorks 2020, you can search HyperWorks CFD, which is this is a HyperWorks CFD 2020, and then you can click. It will open like this. Okay, this is a interface for the HyperWorks CFD 2020. Okay, I will briefly explain what is the function in the HyperWorks CFD 2020. It's quite different if you use the uh, version 2017, because 2017 will use HyperMesh to set up the HyperWorks CFD simulation and then run using the Accusoft solvers. Okay, but for version 2020, you already the HyperWorks Alter HyperWorks already use one platform software, which is call it HyperWorks CFD. So all the CFD simulation, like a model setup, meshing, boundary condition, you will set in the HyperWorks CFD 2020. Okay, so this is quite similar to the Inspire interface. Okay, but different function. Okay, this you have a path browser here. If you import the model, you can have the path browser here. Seems like a solid thinking Inspire. And then you have a setup browser. Okay, we have a boundaries, domains, groups, initial condition, libraries, materials, until mesh control, motion, output, periodics, and radiation. Okay, so this is a view for the view function. Okay, you have a one to view, geometry visualization, mesh visualization, model color, okay, orientation, fit, and also section card. Okay, in the tab view function, we have a file here. Okay, if you want to import the geometry, you can import the geometry file from the CAD data, or you have a hypermesh model.hm, okay, or geometry model, or solver deck. And we have a help here if you want to see the tutorials, whatever lah. Okay, kat sini. Okay, and then we have a edit function. Okay, if you want to undo or redo. Okay, we have a view. If you don't have open up the path browser and the setup browser, you can click on that. Okay, and then for the geometry tab, okay, geometry tab, we have a function like a measures, move, and also grouping your punya part, and then you can convert CAD to the FE geometry. Okay, you can convert, and then we have a red mesh. Okay, remesh the salted model. Okay, is kita jarang guna lah yang benda ni, fix, edit. And we have a surface. Okay, if you want to check the surface, let's say your geometry is not in good condition, maybe ada koyak ke apa semua during you punya geometry modeling, you can repair it. Okay, and then you can check the solids. You can create a geometry surface, okay, like a solid thinking Inspire. You can split, stitch, okay, imprint, drag, sprint, boolean, plug. So, and then we have a function to validate. Okay, supposedly if you import the CAD geometry, you need to validate first. Is it your geometry is suit not for run the CFD simulation or not? So first thing, you need when you import the CAD data, you need to validate your CAD data first. And then next we have a flow analysis. Okay, if you want to run the flow analysis, you can use this flow tab. Okay, this is a parameter simulation setup. Okay, if you click on that, this is a simulation setup for flow. Okay, in the time you can set it as a steady state or transient. Okay, or transient. And then we have a flow type, which is you want to run the flow in the laminar type or turbulent type. Okay, in the turbulent type, you have a several function of the turbulent calculation, which has a For example, is we have a Spalat Almaraz SST, okay, standard K epsilon, K omega, and whatever, and so on lah. Okay, basically, what we usually use is a Spalat Almaraz for the turbulent models. Okay, and we have a heat transfer. If you want to include the heat transfer, okay, the thermal analysis, okay, you can include this heat transfer, multi-fluid, okay, and then we have a solver control here. You want to set as a steady update factor, active equation flow turbulence, and also reference value. Okay, and we have a material library here. The function of material library is a material assignment. Okay, so we need to define thin solid, porosity, source and reference frame. And this is a quite important icon, which is we want to define the inlet. Okay, in the CFD simulation, you need to define the inlet area and also the outlet area. Okay, the inlet means that where the fluid or air or gases flow into your parts model. Okay, and then the next function we have, you need to set up as a outlet. Okay, this is two important icon that you need to use. Okay, the first is the inlet profile here, the profile inlet, and also the outlet. Okay, if you don't define these two, okay, inlet and outlet, so you punya simulation model is not going to run, because it's not, you don't have any inlet and also the outlet of the model. Okay, and then we have a constant. You can define the constant velocity inlet. You can define or assign the pressure. Okay, so this is a far field condition, atmospheric. This is a slip wall condition. Ni kita jarang guna lah. And also we have, you can use the symmetry. If your geometry is half, okay, it's not the full model, you can assign as a symmetry, so that it will duplicate the other half, so that it become the one model. Okay, so this is a function of the symmetry. And then we have a function of radiation. So saya tak cover pun dalam chapter ni. Okay, but you can use hyperwork CFD to run the radiation. Okay, radiation. If you have a analysis that related to the radiation, you can use this. And also you can have a motion. Okay, motion that the motion multi-body dynamics that involved in the CFD simulation. Okay, and also this is a mesh tab. Okay, so you need to meshing it. Okay, you need to mesh. You can use the batch mesher here. Okay, just this automatically meshing your models. Okay, if you click, oh, this is not have a model. And also we have a simulation here. Okay, if you want to run the simulation, you just click on run, and then you can plot the graph of the simulation. Okay, I will start with the example of the T-joint. Okay, the T-joint here. You can go to the file, open up hypermesh model. Okay, so you can choose the tjoint.hm. Okay, tjoint.hm. So this is a T-joint here. Okay, this is a surface. Okay, this is a surface. If you see, this is a surface. This is a section cut. Okay, this is a surface. But in the hyperwork CFD, you need to close the surface to become a solid, and then baru you boleh run. Kalau you have just only the surface, is cannot assign the material. Okay, you cannot assign the material. Okay, how you, first thing that you need to do is you need to validate your surface. Okay, so you go to the geometry tab, and then you click on the validate. Okay, so it will validate your geometry surface, and then it will appear this surface checks and solid check. Okay, so in order you to run the CFD simulation, you need to have a surface check 0 and also solid check 0. If you have 1, means that your geometry have a error or it's not the proper geometry. Okay, you click on that. Okay, and then it will show you the problem. So this is not the closed shell. Okay, this is not a closed shell. So free edges are 0, non-manifold edges 0, self-intersection 0, silvers 0. And then you click on the closed shell, means that your geometry is not closed. Okay, it's not closed. You click on that. Okay, you fix. Okay, it will automatically fix. You need to close the shell, so you click on the create all. Okay, you click on the create all. So it will automatically close the surface. If you click on the validate again, it will appear surface check is a 0 and also solid check is a 0. Means that your geometry is a closed surface. Okay, it's a closed surface. You can use this geometry. Okay, for mouse, it seems like solid thinking. Okay, for mouse, if you want to rotate, you just click on the center scroll. Okay, you can rotate. If you want to translate, you can click on the right click mouse. Okay, if you want to rotate, if you want to zoom, you just scroll. Okay, you just scroll. Okay, after you finish checking the geometry, you need to set up for this simulation I want to run the flow analysis. Okay, flow analysis. Here the flow of the fluid came to this surface area. Okay, this is a first inlet, and also from here this is a second inlet, and also for the top hole here is a outlet. Okay, we have a 2 inlet here. This is a first inlet, this is a second inlet, and also this is a outlet. Okay, so you need to define first. Okay, and then you click on the flow analysis flow tab. Okay, you can set up the simulation model. You click on that. So the time I want to run in the steady state. Okay, it's not transient, the steady state first. And then the flow, I want to run the flow in the turbulence model. I choose the Spalart-Almaraz model. Okay, and also solver control. I don't want to run in the thermal analysis, so I don't check the heat transfer here. And also solver control. Just put it as a default, 0.6 as a steady update factor. Steady maximum step is 100, and also you activate the flow and also the turbulence. Okay, so you just close it. Okay, next you need to assign the material. Okay, you just click on the material assignment, and then you click on any surface of the T-joint. Okay, any surface of the T-joint, you click on that, and then it will appear the dialog box of the material type. Okay, we have several type of the material. Okay, the first one is air. Okay, water, SAE hydraulic oil, aluminium is a solid, stainless steel. Okay, what I want to choose is a fluid, which is a water. Okay, you click on the water, and then you click tick, the green tick here. So it will assign this this T joint that flow is a fluid or water. Okay, it's not the gases or air or solid. Okay, so you already define the material that flow in the T joint, and then you need to define the inlet and also the outlet. Okay, so first we need to define the inlet first. You click on the profile here, so define the profile inlet. Okay, you just click the first inlet surface area. You click this, it will appear the average velocity. Okay, for example, I want to put it as a 1.5 average velocity that flow in the inlet. Okay, you click on the green tick here. Okay, at the setup browser, it will appear the inlet. This is the first inlet at the boundaries. Okay, this is the first inlet. So you can, if you want to change the parameter, you can right click edit, so you can change the parameter for the average velocity. Let's say you want to put the 2.0, so you can put it. Okay, alright. Okay, next we want to define the other inlet. Okay, you click on the profile, you click on the other side of the inlet. Okay, for example, I choose average velocity is a 1.0. Okay, 1.0. Okay, you click on this, and then you already define the first inlet and also the second inlet. Okay, in the boundaries here, first inlet and also the second inlet. And then I want to define the outlet. Okay, I want to define the outlet. You click on the outlet, you click on the top surface here, and it will appear the properties of the outlet. Basically, we put the static pressure is a 0, pressure loss factor is a 0. Okay, if you have your own parameters for static pressure and also pressure loss factor, you can input it here. Okay, you just untick the hydrostatic pressure and backflow condition. You just click tick green area here. Okay, we already defined the inlet 1, inlet 2, and also the outlet. You already defined the material, and then you need to prepare the mesh. Okay, you need to prepare the meshing. Okay, you already set up about the flow analysis here, and then you go to the mesh tab. Okay, you can click on the batch. Okay, you can click on the batch here. So this is the batch measure. So you just choose the surface plus volume mesh. Okay, so it will meshing on the surface and also the volume mesh. Okay, the solid mesh. So this is the average element size. It's quite big, 36. Okay, you can put it as a 5 mm. Okay, 5 mm, or the desired element size that you can suitable for your geometry. Okay, I put it as a 5 mm. I put by default size factor, geometric feature angle, mesh growth rate, and then you just the other parameters you just put as a default. Okay, after you put the average element size 5, you just click on the mesh, so it will automatically meshing your parts. Okay, so it will appear the dialog box here. Okay, this is a hypermesh T-join, run ID, and also the progress. Okay, the progress. Okay, it's already completed. Okay, you close it, and then it will appear the meshing. So the meshing with the 5 mm element size. So this is a solid mesh. Okay, this is a solid mesh here. If you click on the section cut here, you add, so you can see this is a solid meshing or 3D meshing. Okay, 3D meshing. Okay, it's a 3D meshing. So you can see. Okay, so this is a 3D mesh. Okay, so after you complete the meshing here, so you can run the flow analysis. Okay, so you go to the solution tab here, and then you click on the run AccuSolve job. Okay, run AccuSolve job, you just click it. Okay, so you can choose the directory of your analysis. Okay, you can browse it, the folder that you need to run it, and you have an AccuRun path here. Okay, this is by default. Processes to run. Okay, and also parallel processing. Okay, serial. You just go by default, and also you untick the automatically defined pressure reference. Okay, you untick, and then you click on the run. You click run, so it will run the flow analysis. Okay, so this is the progress of your run. Okay, your running analysis. Okay, let's say after you complete it, okay, you can right click. For example, I already run this. It's quite take a longer time to run. Okay, after you complete, for example, here the status will show the green tick icon here. So you right click here, and then you choose visualize in AccuField view. Okay, this is how you want to see the result. Okay, for the post processing, it actually you can open it in the hyperview. You can open up using the log file .log file, but for, I don't know, for the student version, it will not appear. Okay, if you import the log file into the hyperview, it cannot open up. So the other ways you can run into the visualize in the AccuField view. So you click on that, you right click. After you complete the job, you right click, you visualize in the AccuField view. Okay, and it will open up the AccuField view. Okay, so this is a result that appear in the AccuField view. This is the interface of the AccuField view. We have a boundary surface here. So boundary surface, basically we want to show the what type of the result. Okay, you can see the parameters of the result here. So, and then here is a streamline. Okay, create or modify the streamline here. So this is a streamline. If I want to create the streamline, the boundary surface here. Okay, this is a iso surface. Okay, basically we use the boundary surface. Okay, boundary surface. Okay, if you want to see the pressure, okay, this if you go to the scalar, this is all the type for the result. Okay, we have a velocity, we have a pressure, we have a volume, velocity magnitude. Okay, if you see the pressure here, click calculate, and also the boundary types. Okay, which is the first one is the wall output, or inlet 1, inlet 2, and also the outlet here. Okay, so you click OK, so it will appear there. So this is a contour for the pressure. Okay, and then you need to activate the legend, which is the value of the pressure. You go to the legend here. Okay, you click on the legend tab here, show the legend. Okay, it will appear this. You click, you shift, so it will show you. So this is the value of the pressure. Okay, the value of the pressure. So basically, if you see the result, okay, the higher pressure is on the inlet area, and also uh, the both inlet. Okay, at the bottom type of the T joint. So basically the fluid flow for from the inlet 1 and also the inlet 2. So the higher pressure will at the center of the T joint, and then it will go up to the outflow here, and the outlet area, because there is quite low pressure here. Okay, so the higher pressure when the fluid enter the T joint, it's quite the higher pressure here. Okay, so this is how you want to evaluate the result file, the result for the flow analysis. Okay, the flow analysis. Okay, so that's all. So thank you very much. Assalamualaikum warahmatullahi wabarakatuh.